Welcome everyone for Cloud Computing and Big Data, our practical lecture 7.1 about distributed deep learning. Today is a very special lecture. We have an invited speaker, PhD student Rocco Sedona, who is actually an expert in distributed training and distributed learning of deep learning networks. And yeah, please, Rocco, continue your second part.
Hi again, everybody. So in the first part of today's lecture, what we have seen is what distributed deep learning is, so that we have two families of approaches, the data parallelism and the model parallelism. I've shown you what are the challenges of distributed deep learning. So again, the problem that we face when we scale our model on a large number of multiple devices, which are both technical because of the increased number of communication operations, but also scientific because of the degradation we might incur if we use large batch sizes. So in the previous slides, I had shown the one of the ways we can actually exchange the gradients and obtain global gradients in order to update the weights of the model. And here in these slides, which is the last one I showed, I've shown in the part 1, is this more efficient method called ring or reduce, which is, by the way, also used by Horovod. That is the framework that I use extensively for my research. So what I wanted to show you in next slide. Why? Okay, interesting. Cannot go to the next one. Yeah, now it goes. So what I wanted to show you in the next slides are actually some techniques that are used in order to address these scientific problems that I was talking about. So the problem of the degradation of the accuracy, or also known as the generalization problem when you use large batch sizes. So an important thing to remember is that when we use large batch sizes, we also obviously do so because we want to speed up the training. So we also have to use larger steps, so larger learning rates. Otherwise, our purpose of using more GPUs would become pretty much useless. And the question that arises then is, how should we decide the learning rate so that we can obtain an efficient training but not incur the problem of degradation of the performances and, for example, the explosion of the gradients? Well, researchers have answered to this question in multiple ways, and I will show you in this slide one of these ways, which is the proposal of a linear policy to select the learning rate. So let's recall what SGD, which is a very famous optimization algorithm that is used, does. So you should recall this from one of the first slides of today's lecture, part 1. So what it does is updating the weights in the next step, subtracting, let's say, the current values of the weights with the product between the learning rate and the basically the loss of the loss function of the gradient of the loss function with regard to the weights of our model. So when you train with small batch sizes, you can do multiple iterations, let's say, to cover a set of our data. But what if, which is represented here by this T plus K, where K actually means multiple iterations. But what if we want to consider just one iteration, but with a larger batch size that would cover the batch size that we would have with K iterations? So how basically do we make this second and third formula the same? So how can we select a learning rate eta hat that makes sense? So what people have suggested, researchers have suggested in this paper, is that we should just select the new learning rate when we use a large step, as the product between the number of workers, the number of devices that we use, K, multiplied by the original learning rate. So as easy as that. Just multiply the learning rate that used in the case where you had your code running on one single GPU by the number of GPUs that you have. However, it has been noticed that this doesn't scale very well, because what happens when you use large number of GPUs is that the learning rate becomes very, very large. And then it's very likely that the training would stop scaling very early in the epochs. So it would just explode. The training loss would explode, and the model that you have trained would become definitely not generalizable and not suitable for deployment on unseen data. So other researchers have proposed later on another policy, which is called square root policy for the selection of the learning rate, which instead of looking at the formula of SGD, what it does is looking at the covariance matrix of the estimated gradients. So what it does is tries to keep this covariance matrix of the weights consistent independently from the number from the batch size that you are using. So given that you have this formula that comes from this paper, they have computed there is a math behind it if you are interested. What they say is how we make these covariance be the same disregarding the batch size that you use. Well, basically, again, here, eta is the learning rate. What we should do is just substituting this eta with a value that is proportional to the square root of the batch size m. So in a way, since the global batch size is dependent on the number of GPUs that you're using, you can see it also, you can scale it by something that is proportional with regard to the number of GPUs, as the two things are very much correlated. So this policy, since it uses a square root, is much less aggressive than the linear policy. So it's much easier to obtain a descending loss, more consistently descending loss, even while using a larger number of GPUs compared to the linear policy for the learning rate, which is something actually very important when you want to scale up to very large number of GPUs. But as I was saying, there is this problem we might incur, that is the explosion of the gradients, and this is particularly crucial in the early stage of the training process. So you should recall it also. I said this also when I was showing you the formula of how backpropagation algorithm works. So that I told you initialization of the weights is very important. Random initialization is very important. But also when you scale to multiple GPUs and then use a larger learning rate compared to the case where you are you have a small batch size on a single GPU, this explosion becomes even more problematic because you're using larger learning rates again. And so a technique that is being proposed and which is very helpful to deal with the explosion of the gradients is actually known as Warmup. So Warmup basically means starting off the training with a smaller learning rate compared to the one you want to reach. So basically, there are two ways you can start with a constant warm-up, but this technique is not very much used, I'd say. Most of the times I see the technique is the gradual warm-up. So in a way, you gradually increase iteration after iteration or epoch after epoch, depending on your implementation, the learning rate, so that you start off from a very low learning rate and you reach the learning rate you want to achieve, so that you can reduce the occurrence of the explosion of gradients in the early stage of the training, and then use a larger learning rate when the training is well into it's already gone through the first epoch, so it's more stable. And then again, once you have reached that learning rate that you want to use, you can adopt any kind of learning rate schedule that you like. For example, a step decay, an exponential decay, or whatever, or even keeping it the same. It basically depends really on the optimization schedule that you want to use. But important thing is to remember, Warmup is using a smaller learning rate at the beginning. So besides these techniques, there are also other ways the problem of explosion of the gradient and of generalization has been tried to be solved and addressed. One of these is the adoption of actually definition, the creation of newer optimizers. I will show you just one of these. There are many, but this I show you because it's based on SGD. So it's based on a very well-known optimizer. And what it does is basically using the same update rule of SGD, but updating, kind of using a local learning rate that is defined layer-wise. So for each layer of the model, you are going to scale your eta, your original learning rate, by this ratio, which is the magnitude of the weights divided by the magnitude of the loss function. And in this way, in their paper, you and others in 2017 have shown that actually the training can become can be done also with much larger batch sizes and much larger learning rates. There are actually also newer optimizers, for example, LAMB, which is based on ADAM, that is another adaptive optimizer, very well known, and MV-LAMB, which is nothing less than and nothing more than the NVIDIA implementation of LAMB. Also Novograd is another one. However, there is very recently a line of research that is claiming that actually these new optimizers might be helpful, but not so much compared to well-established optimizers, as long as you do some hyperparameter tuning on the parameters, on the hyperparameters of those well-known optimizer. And here I've put this table tree from this paper of researchers of Google Brain that show that actually with proper hyperparameter tuning, Adam can reach and even beat LAMB, which is a very advanced optimizer, as I was telling you, for batch specific for large batch sizes, and Adam, which is a very well established and much more traditional, let's say, algorithm, can beat it as long as you do proper hyperparameter tuning. And this is very interesting, actually, as as our frameworks that we use for the frameworks that we use for distributed deep learning actually now come with embedded hyperparameter tuning features. So this is something very interesting also for our research, I would say. But it's not just about optimizers. I had seen some papers, but also Morris recently pointed to us to this paper from which is called Pollux, is a dynamic scheduler for distributed deep learning jobs. And what it does basically is computing, is trying to find the hyperparameters that are optimal, again, for training with the lesser number, the lesser amount of effort, I would say, in terms of computation. And one of the ways they do it is also dynamically trying to increase the batch size instead of decreasing or using some complex scheduler for the learning rate. However, I would say that in this field, research is really going on at a very fast pace, and it's really, really interesting to see how things will evolve, I would say. This is something I really look into. So before I talk about Horvath, I wanted to tell you that there are also, I've talked about the scientific issues, but there are also as I was telling you, technical aspects that one have to consider that is again the number of communication operations that one have to perform. And there is this interesting concept that is called Tensor Fusion that basically says, tries to pack the gradients in order to make them, let's say, to reduce the number of communication operations that one have to perform. And for example, Horvo, that is the framework about which I'm going to talk in the next slides, offers an inbuilt feature to optimize to use this Tensor Fusion technique that can dramatically speed up the training, reducing the number of communication operations. So now, as I was saying, I will switch to the frameworks part, which is maybe more applied and more interesting for you, but still it was obviously we had to also introduce some theory behind it. So as I was telling you, Horvod is the framework about which I'm going to talk most extensively. It's also because I've used it a lot, but also because many people, not just me, have used it a lot. So Horvod is a framework for data parallelism. So again, data parallelism, it means that we are distributing a copy of the model on each GPU, and then feeding the models with different chunks of the training data. It does it with the ring or reduce algorithm that I've shown you. So getting rid of the central parameter server, which would be a single point of failure in the framework. So it does this with the ring or reduce, which is very, very efficient. And it is based on the MPI and Nickel libraries for communication. I will go through in some slides about MPI and Nickel for those of you who don't know them, maybe because MPI, not all of you have already taken the course by Morris, the HPC course. Otherwise, for those who have, it will be just a very, very basic and simple recap. So Horvod till yesterday or some days ago, it was synchronous. But it seems that in these days, they are going to release a new version 0.23 and very soon version 1, which will introduce new features. And it seems that it will also it will become open also to asynchronous training, which might be something interesting again if you have, for some reason, if you have to adapt the training depending on the resources you have available dynamically. But till now, there was not this feature, and I think not so many users required it. So let's see if this becomes helpful for us in some way in the future. But the great thing about Horvod, despite the fact that you don't have to add many lines of code, is that it can work on top of many of the well-known frameworks for deep learning that you might already know, like Keras, TensorFlow, PyTorch, and also Apache MaxNet for cloud. So again, a relation to cloud and to the cloud computing course. And now, from last year, Horvod has become much more stable and also integrates embedded the ray trace framework for hyperparameter tuning on multiple GPU devices, which is also something very interesting. Because again, as I was telling you, there is this new line of research claiming that hyperparameter tuning is crucial for to obtain good accuracy when you deploy the model on unseen data, so for generalization. There is not just Horvod, obviously. There are also inbuilt solution in TensorFlow or PyTorch for the data distribution, but they are very similar to Horvod. Now I'd say that the technology is converging because these solutions are becoming very, very much similar independently on the framework that you consider. There are also other newer, for example, also in Germany, we have this, pardon my Italian accent, Tarantella, and also HEAT by the Helmholtz Institutes Association, actually. that try to provide similar features, but I would say they're all converging towards very, very, very similar characteristics. At least this is my opinion. But I want to show you again a connection to cloud, and it is the Horvath Runner API. So actually in the cloud, for cloud computing, Horvath comes with two different APIs. There is one which is already embedded into Spark, and there is this other one that is more general, I'd say. Last year, I burnt all my credits on Azure trying to use it. So yeah, but this is very very interesting, because you can see in this figure how this is done. So how Horvath works actually on the cloud, and it works in this simple way where you instantiate this Spark driver that takes care of basically pickling, so serializing the functions and that you have, and you send them from this driver to all the workers that are called executors here in this nomenclature of Spark. And so you can, with the use of this embedded MPI, exchange the gradients, and so train the models in a data distributed setting. So again, this is very helpful, because nowadays it has become easier to access these cloud resources. But I will make some final consideration on the cloud resources in my last slide, because I think this is also interesting to justify that also people like us who work at HPC centers still make sense to exist. But here I wanted to justify with this slide 30 why it makes sense to use Horvath instead of other frameworks. And it's basically because you don't need to refactor your code. You just need to have your code, your PyTorch or TensorFlow code, for example, that works on a single GPU, and you need to just add 7 lines of code to port it to a solution where to a setting where you have multiple GPU devices, which is something very, very good. And then if you want to run it on some cloud instances, it's nothing more than that, provided that obviously you have all the libraries installed, because you just have to add these lines. Here I put an example importing it from the Spark DL, which includes the Horvath Runner API that has all the routines of Horvath, and you just basically need to initialize this Horvath cluster with the number of processes of workers that you want to use, and basically that's it. So you add these 7 lines of code, you instantiate your Horvath, you initialize your Horvath runner, and you can run a Horvath on multiple GPUs on your, for example, I don't know if you have already seen the Amazon AMI machine instances, but you could do it theoretically as easy as that. Okay, as I was saying, some of you might not already have followed the course by Morris about HPC, so it might be good maybe to see again for those of you who, well, for the first time, for those of you who have not seen it, what MPI is. So MPI again is a standard. It's not a library. So MPI is a standard in the sense that it defines some ways, I would say, how to define the communication between different workers into a setting which is known as distributed memory. So that can mean distributed memory can involve the presence of different machines, so not shared memory, not a shared memory setting. And it defines actually either point-to-point, but also collective communication with which you can define also, if you play around, complex or simple topologies like a ring which is important for our Horvath, as again, a ring or reduce is based exactly on the ring that you can define on the ring topology of MPI. but you can define also something more complex where you have a central master node and then the workers around the wheel, or some random connections or whatever you like, even subgroups or subsets of the workers. And that's very interesting. But as I was saying, MPI is just a standard, and there are some multiple MPI implementations. So some of them, for example, Open MPI, or the one by Intel, which is MVAPISH, or also one that we use a lot at the Research Center Jülich is Parastation MPI. So again, the real implementation then can differ depending obviously on the developer. Yeah, so now I will recall some of the operations. So as I was saying, MPI is this standard that defines how to exchange data between different processes. And basically you can do it, as I was saying, with the very simple is one-to-one, but more, I wouldn't say advanced, but maybe comprehensive operation is the so-called broadcast. That is a collective operation that sends data from one process, the same data, the same array, let's say, for example, from one process to the others. So as you can see in this figure, then we have a scatter, which is different in the sense that you send from one process to the others different chunks of the data. So not the same as before in the broadcast, but different data to each of the other processes. Then you have the gather, that in a way it's the inverse operation, where you kind of collect data on one process from the others. And yeah, I'd say that about the collection, that's it. But then once you collect your data, you can perform some operations. It's called the reduce operation. So you collect and then reduce. It means that you, for example, can sum, or you can average, or you can compute the product of the data that you have collected. So again, this is very important. If you recall what I was saying about the ring or reduce algorithm, which now after these slides about MPI should become more clear, even to those who didn't know what MPI was beforehand. So the exchange of messages and the reduce operation, which in Harvard is the average of the gradients that you collect from the local GPUs in order to compute a global gradient. But there is not just MPI for exchanging messages. And in fact, a library that is widely used nowadays is Nickel. Nickel is specifically designed to work with NVIDIA GPUs. And what it does, if you look at the bottom figure, is that it actually can speed up significantly the exchange of information if you use as infrastructure, for example, the InfiniBand interconnection compared to MPI based on the same hardware, actually. So this library can actually work really well. And this is particularly not noticeable actually above, where you have the NVLink, which is a special hardware communication that is used inside islands, I'd say, of GPUs by NVIDIA. Here it is shown with 4, 6, and now I think that A100 can use even islands of 8 GPUs nowadays, and these can significantly boost the performances of intra-node GPUs. So intranode, by intranode I mean GPUs that are hosted on the same node, while the figure that you see below relates more to internode, so to GPUs that actually are lying on multiple nodes on multiple machines, connected, for example, with InfiniBand. And you can see InfiniBand is the speed up is quite consistent compared to Ethernet, which is this one. I want to tell you also one more thing about nickel. So you might wonder if there are competitors to NVIDIA. You see, I've been talking a lot about GPUs and I'm implying that NVIDIA is the one to go and the only one. But actually now also other companies are trying to enter this share of to gain its share of market into the GPUs. And for example, at the Barcelona Supercomputing Center, they are setting up customer test environment for HPC, where we use, instead of NVIDIA, they use AMD Instinct, the AMD Instinct GPUs, and they're trying to see how they compare to NVIDIA, especially because it's not just hardware. Again, as I was saying, you see here this nickel, it's also about the libraries that you use. So it will be very interesting in the years to come to see how this, let's say, this battle between these competitors will be, and if it will bring something good for us researchers. At least we hope so. But this was just for you to have an idea or an insight into the market of GPUs for HPC, which might be also something interesting for you. Then I have these slides that presents a very simple application. Well, no, it presents an application that we developed with a simple ResNet 50, but the application itself is not simple at all because we were using a multi-label setting. So multi-label means that we had multiple labels associated to each of the patches that we used for training and for classification. And also, this is a multispectral setting where we don't just use grayscale or RGB, but we use actually 13 bands, 13 Sentinel-2 bands acquired by a satellite in order to classify the patches that we had, and they come at a different resolution. So we had to kind of adapt the ResNet 50 backbone to our own needs. We use this backbone, the ResNet 50, because it is a very well-known and well-established CNN. Nowadays, we are also using more advanced networks like EfficientNet, but still that can use a less smaller number of parameters, but still ResNet is still a good way to compare results as a benchmark. And so the problem that we were facing was that we were using a very large batch size. And so we had to implement many of the techniques that I've shown you, like the way to decide the initial learning rate, the scheduler for the learning rate, the Warmup, in order to obtain a very good scaling while using a large number of GPUs. And as you can see, we managed to reach actually 128 in this paper, but actually more recently we also reached the 256 GPUs using more advanced techniques, as I was saying, so more advanced optimizers. And I'm planning to also investigate more into these. So before ending our lecture, I wanted to tell you that there is not just Orvod or the native implementations of this data distribution by TensorFlow and PyTorch distributed, but there is also DeepSpeed, which was actually released last year by Microsoft, which would be a very interesting framework for not only data parallelism, but also model parallelism. So for distributing also the model itself onto multiple devices, which is actually a wrapper around PyTorch. So it would mean that adapting your PyTorch code, you would be able theoretically to use not just data parallelism, but also model parallelism and also more advanced techniques, such as the zero optimizer, not in the sense of backpropagation. Here, optimizer means something related to the memory. So the way you optimize in the sense that you can use larger models, actually. And with these, they actually were aiming to democratizing, as I was saying, the access to larger models. So meaning that you could train much larger models onto one GPU only, or on a smaller number of GPUs. And plus, it also comes with other feature, which are the mask for attention. Attention is very important because it's very widely used by these new transformer methods that are very very important for natural language processing, but now are starting to be deployed also for images in the computer vision community. And also has its own ways of reducing the amount of communication operations that it's done. For example, implementing this 1-bit Adam optimizer, this time optimizer, in the sense of a real backpropagation optimizer. But to our experience, myself, also Marcel, and other people at JSC have been trying to use DeepSpeed and to install it with the help of the support team of Helmut Say Hi. But till now, we have not been really able to scale this onto multiple nodes. So for us, still DeepSpeed didn't keep up to its promises, honestly, and we are still trying to understand if when it will become more stable, because this happens all the time. So DeepSpeed is obviously a much more recent solution. So obviously these releases are still in a way very not very stable, and they are still fixing many bugs, and there are many issues with the compatibility between the libraries. And so I guess that it will become very interesting for us once it will work as expected, I would say. There is a last slide I want to show you before finishing, and it's this very simple computation that I did is to try to explain you how much actually training the very large models, for example, this GPT-3, there is a very large model of almost 200 billion parameters by OpenAI, released last year. Now, some days ago, Microsoft actually released a model also trained in collaboration with OpenAI with more than 500 billion parameters. And I took these prices from the Azure website, where you can see the pricing of the different instances that you can request them. And if you do a very simple computation, trying to see how much it takes to train GPT-3 on a Tesla V100, it has been estimated that it would take 355 years. If you multiply this and try to understand how much it would cost, you see that the amount would be quite significant. And I used actually a very low pricing. So the best case where you can get the savings using the GPUs where they are not used by others. So this very special pricing that actually would probably not apply if you wanted to. And in fact, if you look at the more recent instance that I could find actually today, I uploaded this last part today in the bottom, where you ask instances using the A100 that are the most recent NVIDIA hardware for HPC GPUs, and you use these islands of 8 GPUs where you have NVLink connection, so the one that can get the most benefit out of Nickel, you would see that the pricing would become 13 hours per hour, or even 10. Well, let's say in the best case, $10 per hour. So multiply this by 10 if you want to use the most recent hardware. So you see that actually cloud is nice. When you're a student, it's perfect, because also Amazon comes with its own AMIs. Libraries are already there pre-installed. And when you work in an HPC center, you always complain about, oh, this library doesn't work. I have to install it by myself. But then when you're a researcher, you say, okay, but would I be able to rent these resources with the funds that we have? And honestly, the answer is no. So this is also a point of view that I wanted to give you from my side. So obviously, if you have any question, I hope you can you ask me even about the lecture or anything else that you're interested in. I've put all obviously the bibliography, and I want also to thank before giving you the mic, all my colleagues from the research group. So thanks a lot to everybody, and I wait for your feedback.
Yeah, thank you very much, Rocco. Very nice lecture. Also, the last slide, of course, shows you really insights into the cost and expensive business of deep learning. Yeah, we are here for questions, everyone. So if you have questions for PhDing at Iceland or to the lecture material of deep learning, now's the time.